order to graph using transformations, first I have to identify the base function. And we know now so many functions. We have linear, we have quadratic, we have the square root, we have the absolute value, we have the cube root, we have polynomial, we have rational, and now we're adding two more, exponential and log. So can anyone give us the base function that I used to create this function? The base function is? One-third to the x. So there is a first transformation as 1/3 to x minus 1, and the second transformation is which is 1/3 raised to x minus 1 plus 2. And now let's see what this means and what this does. This one is a transformation on the base function, and this one is a transformation on number 1. So what does this do to this function? Is there a change in x or a change in y? So we are changing in x. So when we change x to x minus 1, what does this do? Very good. Now, this is not a change in x. This is the same, but we're adding outside too. So what change will that be? What transformation will that be? Excellent. Thank you. So we are ready now to graph. And now I have to think, how do I graph 1/3 to the x? Because that's my first step. I have to graph the base function. So we know now, looking at what we just graphed a minute ago, we know now that there are two possible shapes. When the base is greater than 1, and when the base is less than 1. Which one is this? Decreasing, very good. This is it. This is a base function, and it has to cross at 0, 1, and this is y equals 0, the horizontal asymptote. Then you told me to shift this graph right 1. Okay, no problem. I'm going to take this point and move it now to 1, 1. Because it goes to the right. Oh, I'm sorry. So now I move this to the right 1. So this graph is 1/3 raised to x minus 1. Now, you said, okay, the next step is I have to take the pink graph and move it up 2. But we established that these two functions have a horizontal asymptote. If I shift the graph up 2, what do I have to shift first? I have to shift the, yes, I have to shift it up 2. So this was 1, 2.
Almost there.
Say it again. Questions?
I'm here.
Okay, perfect. So now I'm ready to present the final graph. So this point now moves up 2. 1, 2. So this is 1, 2, 3. This is 2, and this must be 3. And here is the graph. This is the final graph. I'm going to do this so everyone knows it's the final graph. So this is f of x equals 1/3 to x minus 1 and plus 2. Can anyone now give us the range of the final function? Remember, for the range of the pure exponential function with no transformations, 0 to infinity. But now this function has transformations. And it's also shifted up. So what would be the range of this function?
2 to infinity.
Very good. The domain doesn't change. The domain is still the same thing. That doesn't change, but it has transformations, and we had to move it up. Two special exponential functions. One that is called common, and the other one that is called natural. The common has base 10. The natural has base e. They are so important that they have their own keys in the graphic calculator. So 10 to the x is, I thought I had a pencil here. Yes, I do. So with the second key, e to the x and 10 to the x are right here. 10 to the x, e to the x. And they get activated with the second key, 10 to the x, e to the x. And of course, you see what happens? The same key is shared, of course, by the inverse function. Same thing here. The square root and the x squared, these are inverse functions. These two are inverse functions. These two are inverse functions. You don't know that, but I'm also showing you the trig functions. These two are inverse functions. These two are inverse functions. And these two are inverse functions. Okay? So very important, base 10 and base e. Now, also, let's suppose we forgot what e is and how big is it. We have two keys, e to the x, meaning it's expecting a power. But there is another key that is the division symbol, with, of course, activated with the second key, with the second function. So this has no power. So if you ever forget what e equals to, you just put the second key and press the division key and press enter, and you will get 2.71 blah blah blah. Now, because as you see, both these functions are exponential functions with base greater than 1, they both will have an increasing shape. One will be closer to the y-axis than the other. This one will be closer to the y-axis because it has a higher result for any x. The other one is a little bit slower. It will be a little bit further away from the y-axis. Because you understand, if x is 2, this is a much bigger quantity than 3 to the second power. So 10 to the second power will be 100, and this will be 9, roughly. So knowing that, now we're ready. Where is my book? Right here. And now we're ready to look at some applications of exponential functions. Any questions before we choose applications? An entire section is dedicated to applications, but before then we have other simpler applications to look at. Okay. So I'm on page 5. Okay, this chapter 4 and section 4.1, page 475, 476. Okay, so I'm looking at 66. On page 475, it's about the nuclear explosion or the nuclear plant in 1986 in Russia at the Chernobyl nuclear plant. Okay, they say about 1,000 kilograms of radioactive cesium-137, that's the name of the radioactive substance, was released into the atmosphere. And they're giving us a function that is 1,000 times 0.5 raised to x divided by 30. X is the number of years since 1986, and they say even 100 kilograms of cesium-137, if they remain in the atmosphere, the area is considered unsafe for human habitation. They're asking us to find f of 80. 80 being the year 2066. So if we add to 1986 80 years, we get the year 2066, 46 years from now. So this is the amount of radioactive substance in the atmosphere in kilograms. X is the number of years since 1986. People had to flee the area because they couldn't be around that dangerous atmosphere. They couldn't live in that atmosphere. So they're asking us whether we can tell these people if they're still alive, if we can tell them, or their children or their grandchildren, if they can go back home, if they want to. So even if 100 kilograms are still of cesium-137, if they're still in the atmosphere, in 2066, we have to tell them, don't go back. You can't live there. It's not safe. It's not healthy. Okay. So first of all, forget about everything and just look at this function. It has a constant, it has a base, and it has a power. A constant is outside. It has no connection between 1,000 and the power. If you want to put in parentheses, you can. It's fine too. What type of function is it? Because now we know a lot of functions. So it is exponential, of course. It's an exponential function. It has a base. Is this base smaller than 1 or bigger than 1? Yes. So obviously we expect this to decrease in time, but we don't know if the atmosphere is safe. Okay, so all I have to do is determine f of 80 and tell those people yes or no. 1,000 e, no, not e, I'm sorry, 0.5, I'm sorry. 0.5 raised to 80 divided by 30. We can do this without a calculator. So let's do this together. Since it's only one value that we are interested in, I don't have to put in the y equals. But if I have more values to plug in, I will always put in y equals. So we have 1,000. Now in the calculator, I have to put parentheses, 0.5. I have to put the caret. I personally have to put it. That's me. And 80 over 30 is 8/3. Close the parentheses and press enter. So it appears that the amount in kilograms in that atmosphere in the year 2066 is 157.49. What do you tell the people whose homes are still left behind there? Or property? It's not safe. It's not healthy. Don't go. Not good. Not yet. You have to wait longer. Because it's more than 100. 100 will be okay, although even that for some people will be dangerous. But according to our function, if the function still holds, if the function is still valid in 2066, I'm assuming that they determined this based on the half-life of cesium-137. So, but if the model still holds, then no, don't go back. Okay. The other thing that I was going to mention, there are two, there is what is called compound interest. When we deposit money in a bank or when we get a loan. Compound interest. And we look at two different situations. One, when the interest is compounded. Compounded means recalculated. Compound interest recalculated. N times per year. So the other option is continuously. In other words, continuously means every second. It's recalculated and reinvested every second. Here it's calculated n times per year. There are two different formulas. You do not have to memorize them. They will be given in the problem for you. Here is one, and we'll discuss what each letter means. A equals P, 1 plus R, lowercase r, over lowercase n, n times T. And the other one is PE to RT. As you see, this one does not have n. N is the number of times we compound the interest per year. So now let's write what each and every variable represents. A, in both, is the accumulated value. Accumulated value. If we deposit a certain amount of money today at a certain interest rate, 10 years from now we have an accumulated value. P, principal. The amount of money we deposit or the amount of money we borrow. Lowercase r, interest rate. I should have written in front, I'm sorry, annual. The annual interest rate. Next one, again, lowercase n is the number of times the interest is compounded per year. Number of times interest is compounded, recalculated per year. T, number of years. Let's look at our first problem here. On page 475, let's look at 56. $475. Suppose that you have $6,000 to invest. Which investment yields a greater return over 4 years? 8.25% compounded quarterly, so you have $6,000 to invest for the next 4 years. Which is the best option? 8.25% compounded quarterly or 8.3% continuously? Okay, let's identify each and every piece of information we have in this problem. So I need to identify what the 6,000 represents. What is this amount?
Principal.
Very good, awesome. What does 4 years represent?
T.
Very good, awesome. And obviously in both cases this represents what it's called.
Rate.
Yes, the annual interest rate. Remember, we cannot use percentages. It's 0.0825 or 0.083 respectively. We have to perform two calculations. One with the formula of A equals P1 plus R over N raised to NT. And the other one with the formula PE2RT. And then compare and see which one is better for us. Okay, so A equals 6,000, 1 plus R for quarterly, 0.0825 divided by how many quarters are in a year? 4. And 4, which is the number of times we compound interest, times the number of years. So 4 times 4, 16. And then we'll calculate this in a moment. The other formula will be 6,000 for the continuous times E. Rate is 0.083. And we multiply it by 4. And let's see what we get. Again, we cannot perform these operations without the calculator. So, allow me to get a sip of water. Got it? Okay. So, we plug in 6,000 in parentheses, 1 plus 0.0825 divided by 4, close the parenthesis, and put the caret. You know me, I have to have parentheses everywhere. It may work without, I don't care. I have to show this because some of you have older calculators, and without parentheses it may give you an error. So press enter. 8,317.84, and the other one 6,000. Remember E with the power is this, E without a power is this. So I need E with the power in parentheses, 0.083 multiplied by 4, close the parenthesis. Because it raises it like this calculator, it may not need parentheses, but I don't know. I don't want to have to go back. So 8362.52. So now we compare. Which one you prefer? The 8.25% compounded quarterly or 8.3% compounded continuously? Which one is better for us?
Continuously.
Continuously. Better for us.